Okay, so Eviden, you've recently been awarded the contract to build a modular data center, I think it is, for the Euro HPC or high performance compute Jupiter supercomputer, a first, I think, exascale system in Europe at least. So just be good to understand, I guess, the background to the winning of that contract, as much info as you can share.
Sure. The modular data center contract was an open tender process, so that meant it was open to anybody who had the capability to build those sorts of modular data centers. We Eviden won because of our proven ability to deliver modular data centers at that scale. Particularly the integration of the HPC technologies into the modular data center. There's a lot of companies out there who have the capability to create modular data centers, but HPC systems are kind of unique in the sense that they have very high density. There's lots and lots of power involved, and the cooling is very particular to them. So many companies don't really have that ability, and so they could build a modular data center of that size, but it would take them a lot of extra time and effort to get to a point where they understood the weights and power involved. And so for those reasons, the contract was awarded to us.
Okay, so having made that point, it'd be good to understand just how substantial is the data center in all its sort of measurements, if you like. So obviously the physical size, the capacity, all the infrastructure. Again, I'm sure you could explain a lot, but just sort of give us a summary of all of the infrastructure that is required to make this project come together, if that's possible.
Sure. When it's finished, it'll be about 75 meters by 30 meters in size, the total thing. But that size is made up of modules that are up to 17 meters by 3 meters. The core size is 17 meters long and 3 meters wide. And the reason for that size is it's the biggest size that you can put on the back of a lorry and ship about on the roads. And that's how it's delivered basically to the customer. So what then happens is that those modules, they're kind of purpose-built, purpose-designed, and then they're plugged together against a sort of central corridor, so that you build up this bigger building, and that gives you everything that you need to host the supercomputer. So it's got data halls, it's got compute rooms, it's got M&E, so that's electrical and mechanical services. It's got workshops. It's got other areas like office areas and that type of stuff, all built into it. There's a UPS area as well, uninterruptible power supply as well, all built together. So when it's finished, it's like a complete data center. We work with local contractors in Germany who make sure that it will conform to all of the normal sort of fire and safety regulations that there are in that part of the world. So that's what it'll look like. It'll basically, when you go into it, when it's finished, it'll look pretty much like any other data center, but it's been built out of these components. It will have the capability of delivering around about 30 megawatts of power. So 30 megawatts is an immense amount. It's more than we need. But we really don't want, Europe's largest supercomputer to be constrained by power. So, we have a margin over and above what we will need.
Okay, and just in terms of what you're supplying, are you supplying a shell in effect which is then populated with all of the cabling, the cooling, the power, etc., or are you also supplying the some or all of that kit when you supply the modules as well?
Right. So it's not if I said a shell, that's kind of not right exactly.
Oh, no, sure.
So what happens is that the the modules are built to our specification by a subcontractor, and then they are delivered to our factory. So the factory is where we build the supercomputers, and so we put all the kit into the modules in the factory. And so each module has its own functions. Some are for compute, some are for data, some are for other services like the transformers and all that type of thing. And by doing all of that in the factory, we can really streamline the process and contract the amount of time it takes to deliver the whole project. It also allows us, one of the issues, if you like, of building a really big supercomputer is it is really big. It's got lots and lots of components, lots and lots of racks. And while you can build and test a rack in the factory, traditionally what's then happened is we've shipped the rack to the site and then plugged it into all the other racks and then done rack to rack testing. By having a module which is delivered to the factory, we can put loads of racks in. In fact, there's like probably 10 racks per module, something like that. And then we can do the rack-to-rack testing in the factory. So you have a much bigger subset of the whole, with which you can do testing, which is testing that you would have to do otherwise on site. And that streamlines the process of actually getting it installed when it reaches the site. So all of those things can be done ahead of time, which as I say, which streamlines it. The other benefit in a way of doing it like this is that all of the services for a module go through the small face, if you like. I said it was 17 meters by 3 meters. So all the electrical power and cooling go through the 3 meter wide entrance, if you like. And what that means is that once a module has reached the end of its useful life, it can basically be unplugged and replaced by new technology. So it kind of makes the whole process of upgrade happen easier and more seamlessly.
Yeah, I mean, I was going to come on and ask about the benefits, but you've obviously described much of that there. So we're talking about sort of flexibility, agility to, as you say, to upgrade as and when, and by pre-populating the modules, you're saving quite a lot of time. And presumably there's a safety angle, etc. If everything's pre-approved in the factory, you've not got lots of people running around on site with all the potential for, I don't know, things to go wrong, shall we say, while they're doing it. Is that fair to say?
Well, I mean, yeah, those things are certainly true. I mean, I think that probably in terms of saving, there's a significant saving embodied by that ability to do all that upfront work. So it costs less, and in terms of the testing, there's something like 240 kilometers of fiber associated with this machine. And now we can't do all of that in the factory, obviously, because the modules have to be connected from module to module, but quite a lot of it is actually inside the module. So you don't have to then redo that. And this is very fiddly business. The whole business of getting the fibers are very, very high performance, 400 gigabit second fibers. And so they have to be tuned really well, so that's getting all of that done can be a time-consuming process. By doing it in the factory, you've done it up front, so that again that streamlines things. I think from the point of view of delivery time, that will really reduce the delivery time to get the system up and running to its full specification. The other point to make in terms of thinking about benefits is that we're using water to cool the system, and in fact we're using warm water to cool the system. So it may sound a bit counterintuitive, but if you can use warmer water to cool the system, then it costs less to get the water. Once you put the heat into the water, it costs less to get the water back to that warm water state. So effectively, you can do it very, very cheaply. And all of that is built into the fabric of the module, if you like, the cooling system for the supercomputer. And all of that adds up to millions of euros of savings per year. So it's a really useful thing, really good thing to have, so that you can deliver the services as efficiently as you can.
Yeah, I was going to ask about the cooling because obviously it's a not insignificant piece of computer, so there's quite a lot of heat being generated. And you say liquid cooling. I can't remember how many different varieties of liquid cooling. Are we talking full immersion here, or are we talking direct to chip? Can you just give us a bit more explanation of the actual cooling process?
Sure. So the system is direct liquid cooled. So that's at one extreme there's air cooling, at another extreme there's immersion cooling. This is kind of in the middle. Basically, the way the system works is there are cold plates, and all of the components are the motherboards, the CPUs, GPUs, memory DIMMs, network NICs are all actually put onto the cold plate, and then the cooling water runs through the cold plate and takes the heat away from all of those components. And what that means is that 98% of the heat from the system goes to that warm water, which is a very, very high percentage. So it's a little bit different from a liquid immersion system where you actually dunk the whole system into a tank. But we think it works really well because it means that maintenance of the system is much, much easier. It's got dripless, quick release interfaces with the cold plate, so you can pull out one of these cold plates if something goes wrong, like a DIMM fails, for example. You can pull out the cold plate and replace the DIMM just like you would be able to on an air-cooled server, which is different from like a liquid immersion cooled system where you have to sort of take the whole thing out and dry it off before you can replace anything. So from a maintenance standpoint, it's really good, but also from an efficiency standpoint, it's also really, really good. And as I say, 98% goes to water, which means that we can have very high density of compute in the system. And the system, modern GPU technology the GPUs are up to 1 kilowatt for each chip. And what that means is that a server will typically have a bunch of those GPUs within it, and so a single server might consume 10 kilowatts. Now that's pretty well, I mean, not quite, but nearly the limit of what you can cool in an air-cooled environment. So what that would mean is you could put only a single server into, maybe two, something like that, into an air-cooled environment. But what we can do with this direct liquid cooling system is we can fit 30 into a single rack. That means that the rack has got to be super high powered, but we can cope with that by the rack design. So for all those reasons, it makes sense to do direct liquid cooling, and it makes sense to do it with the warmest water that you can use, or that you possibly can, because it makes it cheaper to get the cooling done.
I'm just wondering, I mean, one of the advantages potentially of liquid cooling is you capture the rejected heat and repurpose it. Is that something that is presumably is possible, but is it being used in this case, or is that not being?
Yes, I mean, so our first goal is to make it as cheap as possible to run the system, but more and more people, as I said, the entire data center is going to be possible to power 30 megawatts. Now that's an immense amount. That's like a town or something like that. And more people are looking to use the power, use the heat that's available in that water to heat things and to do other things with that heat, and that makes them more efficient still. So it's a big focus for Julich, for the center where the Jupyter system's going. It's also a big focus of activity for ourselves. We want to achieve net zero as quickly as we can, and so we're supporting Julich in that effort. and they have a campus of 7,000 people. So it's quite a big area in the countryside, and it takes megawatts of energy to provide heating and that type of stuff for all of the buildings that are on the campus. And they're going to use the rejected heat from the Jupiter system for that purpose. So yes, it will actually make things greener from that point of view as well.
Yeah, and I was going to ask it in terms of the client. I mean, sustainability. You've explained sort of part of it there, but I guess was that a big sort of focus for them and yourselves? And also, I guess just more generally, how involved were they in the specification? I mean, when they said, deliver us a modular data center, did they then kind of say up to you, over to you, or did they get involved in the specification of parts of the infrastructure? But just how that partnership worked, I suppose.
But yeah, they're very, very closely involved with us with the design of the system of the MDC and of the supercomputer. So one of their kind of core goals in life is conserving natural resources. So that's their research activity, but they aim to demonstrate it as well by their what it is that they do. So they don't. They're never going to go out and get the most energy hungry machine that they can because of that kind of core principle. And HPC, who provided a lot of the money for the Jupiter system, have the same goals and aspirations as well. So yes, they did work with us very closely on defining how the system would be, how the supercomputer would be, and how the MDC would be, the modular data center would be that goes into it, so that it would meet those combined goals.
Okay, and in terms of, I was going to, well, yeah, I'll ask first about modular data centers more generally, and then we'll just maybe finish off around the supercomputer itself. But in terms of modular data centers, I mean, it's clearly been a growing trend for a while. I just wonder if you can perhaps sort of summarize the thoughts as to, you've obviously explained the benefits in this case, but modular versus what we call traditional bricks and mortar. I mean, is modular on its way to eclipsing traditional bricks and mortar, or is it very much each project? It might depend. Just your thoughts, I suppose, as to how those different approaches are going to coexist or not, into the future.
Well, we see that the desire for modular data centers is certainly growing. There are some people who still think that traditional data centers are the right way to go, but the issue for that traditional approach is that these machines are getting more and more complicated with each generation, bigger, more power hungry, all that type of thing, and so it kind of makes sense to do it in a modular way, because otherwise you essentially have to refit your bricks and mortar data center with each generation of supercomputer. So by changing the module, you don't have to do that. And another really big factor is the available power, and we see situations where traditional HPC centers do not have enough power, because these systems are growing in power requirement every generation, and so what we see is that quite often traditional data centers don't actually have the power available to them to power the hungriest machines. And the consequence of that is, sometimes in order to get new power to a site, it will take sometimes years to do that. And you have to get permission from the local authorities. You have to get the power company to put the infrastructure in. Quite often, the data center is not really a priority because they have lots and lots of other priorities. And then there's all the business of digging up roads and practical things like that to put new cables in. And so one of the trends that we see is traditional HPC centers saying, well, actually what we're going to do is we're going to go to where the power is and put an MDC there, have like an outpost of our data center there. So the expertise remains where it was, but the actual data center, which can essentially be more or less lights out, is in a different location. And that way you kind of get the best of both worlds.
And it sounds as well, I mean, if you're delivering a supercomputer, as you explained, the maybe people's worries, or once upon a time modular, it was difficult to pre-populate with loads of racks and cabinets, and so it just wasn't capable of being transported with all that kit and weight inside it. But now you can pretty much cope with any kind of internal requirements and deliver it in a modular format. Is that right?
Nearly. I mean, what we do is in the factory, we put all the racks in place. We populate them all with the blades, etc. We do all the testing, but then we take the blades out again because they are in fact too heavy. The racks really are too heavy to be transported by road. So most of the weight is in those blades. So we take the blades out, transport them separately, and then the module can be taken to its final destination on the back of a lorry, and the blades get transported separately and put back into the rack when it gets there. Because otherwise the vibration would make things perhaps rattle loose or something. I'm not sure.
Okay, and maybe just finally, we talked a lot about it's an exascale system. To just be good to understand. I think yourselves are also supplying or have supplied the supercomputer. So it'd be good just to understand the spec and what the applications, typical applications, is going to be useful.
Sure. So the spec, yes, we did supply the supercomputer, or we will be doing that in combination with the MDC. In total, there's around about 24,000 high-end GPUs that go into delivering the computing power for this thing. And it's really the function of it is really to serve a wide range of scientific goals. I mean, I spoke a little bit earlier about what JSC is set up for, the Julich Centre is set up for, but it's really a wide range of different applications across different scientific disciplines. So things like weather forecasting, getting more precise understanding of what the weather's doing, when there's going to be extreme weather events, how the climate's being changed. Obviously, climate change is a really big deal. So that's a big research area that they have. They do a lot of work on digital twins for manufacturing. So they're trying to work out better, more efficient ways to build things in the manufacturing process. So that's partly material science, and it's also partly the way in which things are fabricated. They have a human brain project, so they're basically modeling the brain. They're trying to get more and more of the brain into their model, so more and more different capabilities of the brain are being modeled on the supercomputer. So it's like, if you like, a different form of digital twin. They're working on personalized medicine. So there's this idea that if you and I have the same disease, maybe your physiology and my physiology will respond differently to different medications, different treatments. And the idea with the personalized medicine is to be able for the doctor to be able to determine which one's right for you and which one's right for me for the same complaint. So that's a big research area. And then, of course, AI. I mean, AI is absolutely huge and getting huger all the time. So this machine will be used for the whole generative AI research area, particularly large language models. We can use HPC equipment to do AI, and that's one of the goals of this machine. That'll be partly things like LLMs on their own, so AI models, as it were, standalone, but it'll also be partly AI as a way of making the tool chain of an HPC, because a typical HPC workflow is not a single job. It's a job that models one part and then another part and then another part. And one of the things that researchers are finding is you might be able to replace one of those parts with AI and get much better results for the whole chain. So that's another area where this system will be utilized. So so far, I think the big AI models have primarily been done on non-European data sets. So, one of the things, the goals for the system will be to use European data to tune models more closely to the kind of data that we have here.
Yeah, and just perhaps finally, you mentioned AI there, and you mentioned earlier the idea of bringing data centers to where the power is. So the combination of those two things, do you think there is going to be, if not a boom, at least an expansion of that type of data center build? Because as I understand it, for this kind of AI activity, location doesn't matter, in terms of latency, because they're sort of doing stuff in the background, which will then be used in practical examples. So do you think that's a significant trend in terms of modular data centers being built where there's some good power availability to train these large language models?
Oh, absolutely. I mean, the same is true for AI and HPC. I mean, you need these big amounts of power, and the physical location is less of an issue. So the fact that it might be 100 miles away is much less relevant than perhaps it used to be. And so I'm talking to people today who want to build big AI systems but don't have the kind of power that they need, perhaps in their university or in their local center, and so they're looking around, and there are hubs where they can go, hubs of the electricity network where they can go, and really all you need is a concrete slab. At that point, so yes, you need some water as well, but you need a concrete slab, some water, and the power. If you go to where the power is, then obviously finding that is much easier, to get somebody to run the cable from a transformer that's sort of just across the way there, rather than having to take cables across country to where the data center might be.
Okay, it's been fascinating to chat, some great insights as to what's going on in this project and more generally. So, Crispin, really appreciate your time. Thanks very
Yeah,
much.
thank you. Thanks very much.